and you're not going to know what normal distribution is. So now I'm going to get into that. So trying to wrap it back to what I went over last week. You'll remember I went over shape of data. So when we have symmetric data, this is somewhat close to symmetric data. As I said, our mean and our median, which are the red and purple lines, are about the same. The outliers on each side are about the same, and in the middle, it congregates in the middle. So that's what we're looking at when we have symmetric data. Normal distribution is symmetric. So that's what you want to see when you look at data, because then if you have a normal distribution, statistical tests can be done. You have to use different methods if it doesn't follow that. So that's a whole nother ball game, but this is what you want to see when you look at data. What you don't want to see is this. So this is not normally distributed, and I'm going to go over the definition in a second. But when we have this long tail of outliers in the right skew, that's not normally distributed. When we have this long tail of outliers in the left skewed, that's what we don't want to see. But that's why that was important. So the normal distribution, if you've ever heard of a bell curve, that's what it is. So I'm going to put a lot of different images of the different aspects of the normal distribution on each individual slide, trying to build on it. So as I said, the normal distribution is symmetric. So the mean, the median, and the mode are, for the most part, going to be in the middle. And as it's showing here, you're going to have about, if you draw a line in the middle of it, you're going to have about 50% of your data on one side and 50% of your data on the other side. So the thing that we were seeing with lots of outliers, there are some outliers in this, but there's about the same on each side. That's what you would want to see. So not all bell curves look the same. And you can see this photo here, or this picture here. Those are all normal distributions. So normal distributions can have the same shape, but as I'm going to go over in just a second, they can have mean and standard deviation, the things we went over last week. It can have a different mean and a smaller standard deviation, or it can have a different mean and a much larger standard deviation, but if it follows the general shape, it's going to be a normal distribution. So this is what I mean by that to some extent. So I'm going to go over more about these concepts today, but now you'll see why I went over them last week. So I'm actually going to walk over and, okay. So we're seeing this, and I'm going to try to explain all these different aspects of this normal curve one by one. So this side is one standard deviation away from the mean in the positive direction. So say this is, and I'm going to show an actual example, but say that this mean is 5 and the standard deviation is 1. So this will be 5, this will be 6, and then when you go over here, it'll be 7 and 8. So each of these lines represents one standard deviation away from your mean. And you'll see the same thing on this side. So you have your mean here, and if you're going back, so if you have 5, it's going to have, this one's going to have a standard deviation of 4 and 3 and 2. So you're going to see that every time you see a normal distribution. So these represent the mean and one standard deviation to the right or the left. So what you're going to see up here, and no matter what your standard deviation is or what your mean is, it's going to look, this rule applies every time, or approximately. It's never going to be perfect with the survey data, but as long as it's close enough, and there are tests you can do to see if it's normally distributed, we'll get to that later. But if it's within a certain range, close to this shape, you're good to go. So within the we have one standard deviation lower. So say, pretend this is 5 again. So we have 4 and 6. About 68% of our data is going to be between 4 and 6. So, and then if you go out one more time to 2 standard deviations. So this would be 5, and it would be 7 and then it would be, yes. So we have that 95%. So between those two standard deviations, it's going to be about 95%. So if we go out all the way to 3 standard deviations away, that's going to have 99% of our data. So all our outliers are going to be here for the most part. So, okay, and back to the central limit theorem. So if your sample size is sufficiently large, no matter how big, no matter what the underlying distribution or another way to say that is no matter what the distribution of your sample is, if you sample it multiple times, so if it's skewed to the left, when you sample small amounts, when you sample large amounts, it's going to look more normal. That's the whole idea, and that's the whole idea of statistics in general. Is when it's normal, it's easier to make conclusions about it. And then what we're going to talk about more, and I'm actually going to talk about p-values next week because there's specific topics that have to go with p-values. And when I went and tried to do that, I realized there was too much information. But the normal distribution also helps you quantify how certain you are that your results that you're giving are correct, which I will get into that in a minute. So this is a real life example. Going back, this is random sampling that samples with a certain mean, a certain standard deviation, and then in this case, we're random sampling 10,000 observations with a mean of 5 and a standard deviation of 1. So exactly the example that I gave you theoretically last time is here. So I know this is small, so hopefully if you have the slides open, and I will again do this. So I'll walk around. I should have made these text labels bigger, so that's it. That's something you always want to look at when you graph. So we're seeing here in every line that's labeled over is 1 standard deviation. So we are seeing that about 68% of our values, and this is randomly chosen to fit this distribution, are here. The length of the arrows. 95 is the length of that green arrow, and 99 is the length of the blue. So this is, and I'm going to show you an actual data set next.
Which one was the line?
Oh, sorry.
The blue line, vertical, or
So each individual line here. So, and I should have made those bigger. So the mean was 5, 1 standard deviation over was 6,
okay.
7, and 8. But the big part is looking at what this looks like. Even though we chose it randomly, since we took 10,000 observations, it's showing that bell curve. If we took 20 observations, it would not show this, more than likely. Or it would be more spiked, and there would just be more random. But when you do 10,000, no matter how many you sample, if it's over a certain level, it's going to look like this. So, and then I color coded here just so you would know which arrow was which. So the top is the 68. The green is 95, and the blue is 99. So, and you can look at how much data is there, and it looks about right. Just by, and then this is a count. So how many mean values are within that bar? So here's 5. This bar right there would say how many mean values were between 5 and 5.1. So those are called bins. It doesn't really, I'm looking more at shape than detail here, so I just wanted to show, but histograms always show some type of frequency. So if you have a count on the side, it's always going to be the frequency of whatever you put in the histogram, whether it's means or standard deviations or count of form. It's always going to. So this is what I am talking about setting the seed. You can choose any random number here. So I set this so your results would look exactly like mine. So in the back end in R, 47 means that they'll randomly choose the same values every single time. It's good because if you code something, it's not reproducible or can't be used again. It's going to be different every time. And say you want to investigate one problem and you don't want to have to kind of start from scratch every time. For this instance, it was so your results would look exactly like mine, but that's what this is. So it will randomly sample the same numbers if you rerun it. So that's why I had to exit out of R, because I wanted to show you what it would look like every time, that it would be different. And if I had the seed as 47, then it would have been the same exact thing every time I ran it. So that should make more sense now.
Is there a reason why 47?
It's a total random. You can choose any number you want. It doesn't matter. Yeah, I just chose 47.
Well, I mean, is 47 something that allows you to make your results like your?
No, it's still random. It's completely random. You just set it because you could choose 1, you could choose 3. It's still going to be random. It just reproduces your results. So I was wondering when we did that, oh, did my code finish running? If there's not a stop sign here, it's done. So in this case, remember I said 30 was the number that you had to pull for each individual sample. So here I will go over this piece of code. So this is an example. You don't have to understand the details, but here this 10,000. So if we go into the middle, we have that sample function we went over. So I took the opioid data that I put into this data set, which is not normal, by the way. It's way skewed towards, so there's really long outliers for states that are prescribed way too much versus states that are somewhere in the middle. So that is not normal data at all. So I then took 30, randomly chose 30 prescribing rates. And in this case, replace equals false is what you want, because you don't want to have duplicates. Because I'm pulling 30 and then I'm starting over. And then I pulled 30 random samples 10,000 times. So that's exactly what the central theorem, limit theorem means. It's absolute, like, word verbatim. So in order to get results that make sense, you have to sample 30 values every time, or it won't show the right result. And then you have to do that a large number of times. Go ahead. 30 values, 10,000 samples. No. Okay. Each time I sample, I take 30 random values. And then I repeat that process. So that's a sample. The 30 values are one sample. And then I create 10,000 samples. So I redo that process.
But 30 out of how many? Like out of
it's 612. So, and here, because I didn't know as well. And we're going to use that a lot more later. Because that does matter, you're right. So it's 612. I just did 30 because that's the minimum, and I wanted to show you it worked. Go ahead.
So just to make sure I understand, you end up with a matrix of 30 by 10,000.
30 columns, 10,000 rows.
Okay.
And it looked like could not find function string detect because I didn't. You should have that one from last time. I forgot to load a library because I kind of forget. Because I always load certain libraries. That was my problem here. String R package was not. So I was getting an error that I didn't get earlier. It's because I closed my R and it said error string detect cannot find function string detect. That means you didn't load the package every time. So a lot of you saw that last time. So that's an example of debugging. And you learn what they mean the more you see them. So now when I rerun, this is the data set we have. So this is what it actually looks like in reality. So if I go down here, you'll see V1 goes out to V30. And then I calculated a mean of the entire row and put it at the end. So that's how I'm doing this example. So the results that I'm going to show you are going to be based on this mean. And that is, again, the mean values of those randomly chosen prescribing rates over there. So, and then if I scrolled the whole way down, you would see that there are 10,000 rows. And the way that you know that, you come over here, this is called normal.df. I come over here, 10,000 observations with 31 variables, and it includes the mean. So that's where you would see there's also functions to output that information, but you can see it there as well.
Is there any limit to select 10,000 or it's just you wanted to?
Yeah, that's the very frustrating part about statistics. So there's no magic rule about this. And when I first started, I got really frustrated because I'm like, well, there's no cutoff. So there are ways that when you actually run analysis, you can see. So this is a great example of something that this would be a test. So say I ran it 100 times. Does it follow that normal distribution? Does it look normal? No. Well, then we probably need to run it more times. So there are ways. We're going to cover standard error today, and that's a way to look and estimate whether your sample size is too small. So you have to use other means because every data set is different. There's not a magic number, unfortunately. I picked one that was sufficiently large that I knew it would work. Go ahead.
It says on the data panel, 1,000 observations of 31 variables.
10,000, but
Or
yes.
10,000, I mean, 10,000 observations. Isn't the 31 need to be 30?
Remember, the mean is at the end.
Okay,
Yeah, so no, you have to do a row mean. But yeah, so that's something and I honestly, I had never used a row mean before, but I Googled it and found it. So I had never seen that function until writing it last night. So that's an example of no matter how much you use this, you don't know everything. And if you're doing something convoluted and it looks inefficient, there's probably a function that does it in an efficient way. So Google it. If you're doing too much work, somebody's already thought of it and fixed that problem. Almost, that's the great thing about R. So if I'm going to show you what that individual data looks like. So these, in a visual way, once it loads, this is what the data looks like. So we have our count values. So I think it helps when I point to what I mean. And I apologize for the text labels again. I won't do that, make that mistake, guys. But the mean in our case, because with our data, the mean was 80, just because that's the data that's there. I'll remind you that the prescribing rates are in number of bottles per 100 people on average. So it's looking, and then the same person could have gotten 10 bottles, and one person may have gotten 10, and it also doesn't take into account the quantity in each bottle, but that's what these numbers mean. So in the most common was 80 prescriptions per 100 people. So, and that's the reason I use that data is because it's shocking. So we're seeing here, all you want to see, and like the granularity doesn't really make sense. It doesn't matter, I apologize. But you're seeing count data here of the means, which is what the central limit theorem says. So we're looking at, for instance, we're seeing here at this 80. So that 1,000 observations had a mean of around 80. But the big point that you want to keep in mind is the data is not normally distributed. But when we resample, it is. That's the main point here.